So, hello to everyone who's watching on YouTube. Since no one has joined the session in person yet, I'll wait for 5 or 10 minutes so that a few people join the session in person. Yeah, so we'll get started in like 10 minutes. Hi Rupa, we'll get started in like 5 minutes. I'm just waiting for a few more to join the session. If no one else joins, I'll start in 5 minutes nonetheless. So around 6:10 we'll start. Okay, I believe no one has joined the session in person yet this time. So I'll just be addressing the YouTube audience for now. So hello to everyone who's watching on YouTube. So um, welcome to I guess this is the fifth session for this is the fifth problem solving session for the NPTEL Games and Information course. And my name is Lakshya Saggi. I'm the problem solving TA for these Monday 6 to 8 p.m. sessions. In this session, we'll be continuing the discussions uh, similar to those which we discussed last time. Last time we discussed Nash Equilibrium for zero-sum games. In this week's lectures, the topics that were covered were like Nash Equilibrium for non-zero-sum games or infinite games, and also about quantal responses in the games. So we have some problems prepared for uh, uh, these topics which are covered, these new topics which are covered in this week. And yeah, I believe this week's lectures were a lot more theoretical in nature rather than like more problem solving oriented. So I would also like not discuss the whole theory, but I would also like just in the starting, I'll like to recap some of the basic things which were done in the lectures this week, so that everyone has a good idea of what we are about to discuss. And yeah, like I'll be assuming that you guys have gone through the lectures, but still I'll be recapping some of the things, and then we'll proceed to solving some problems related to this week as always. So yeah, the problems will be more theoretical in nature today because of this itself, that the lectures were theoretical. Okay, so Satish has just joined the session in person. So hello Satish. I was just about to start. So yeah, I was just saying that today's session will be a bit like, so we'll be discussing some problems in this session also, but I'll also be recapping some of the theory which was discussed this week. Like not in detail, but just the high level idea of whatever was discussed this week because there were a lot of proofs involved this time around. So yeah, so we'll be first recapping some of the theory and then we'll head on to some of the problems. And I believe problems are not that difficult if one understands the theory for this week. So I'll just start sharing my screen and we'll start discussing the problems. Also, that these like at any point of time, uh, if you believe that if you feel that you have any doubts or you are not able to understand something, feel free to ask me via chat. Or if there are any technical issues, then also inform me. Like I'll try my best to rectify them. So I'll just start with sharing my screen now. Okay, so I hope my screen is visible. Yeah. So yeah, I guess we can get started then. As I discussed, this is the week 5, and what we'll be assuming in this week is like this is a standard convention. Like you can take any convention, but just stressing it out that in a non-zero sum game, the column player will maximize their payoff, and yeah, while in a non-zero sum game, both players aim to maximize their payoffs. So like what I'm trying to say is that in a zero-sum game, we assume that column player is maximizing his or her payoff, but in non-zero-sum game, we'll assume that both players are aiming to maximize the payoff. And like, why are these assumptions different for zero or non-zero? Like, it's just a very standard convention. It is not really a very big convention, but like column player is maximizing the payoff in a zero-sum game. This will imply, since the game is zero-sum, that the row player will be somewhat minimizing his or her payoff because it's a zero sum game if we are assuming the same matrix. But in non-zero sum game, we'll have to assume different payoff matrices for both row players and column players. So we'll just say that both players are aiming to maximize the payoffs. Like it's really just a notational thing, not something to worry about. But yeah. So I guess we can get started. First, we'll discuss some of the recap of whatever was discussed. So this week in this week's lectures, the first set of things which was discussed was non-zero sum games in a finite strategy space. So suppose there are like n agents, let's say like a bounded number of agents, but and each agent has finite number of strategies, not infinite strategies, but rather finite strategies. And but the game is non-zero, so sum of utility is not equal to zero, as we discussed last time. Here we proved everything using linear programs and all. This time the game is a non-zero sum game, so this can be modeled like these are just like snippets from the lectures only. So in a non-zero sum game in a finite strategy space, it can be modeled as a, suppose we have a set n of the n players, and then we have a set Si of strategies, where the set Si denotes like set of strategies of the player Pi. And these are what I'm calling the what, and this set I will refer to using the pure strategies. These are not mixed strategies. So in a finite strategy space means that in a finite pure strategy space, the number of pure strategies are finite. So this set Si is bounded, and that's why we say like this is finite. And then there will be some utility functions for each of the strategy profiles. And this utility will be different for each of the players, right? This utility will be different for each of the players because this is a non-zero sum game, so uh, utilities won't be correlated. So we'll have utility of player I in a strategy profile x1 to xn will be equal to nothing but cost of pi when uh, player profile x1 till xn. And then mixed strategy, and then what we call is as a mixed strategy. Mixed strategy is nothing but a probability distribution over a set of pure strategies. So a mixed strategy for pi is just a probability distribution on the si, which is a set of pure strategies. So yi is nothing but the set of mixed strategies, capital yi, and each of these elements will be just belonging to. So each of these elements will be a vector of dimensions si. It will have SI dimension, basically the size of SI, because like each vector yi will denote that each entry of this vector yi, small yi will be a vector, and each entry will denote the probability with which we are playing that specific strategy. So there are like capital SI pure strategies, like mod SI pure strategies, and now this vector yi really just denotes like with what probability are we playing which of the pure strategies. So since all of the entries of this yi vector are probabilities, so probabilities will have to be non-zero, and sum of probabilities will be equal to 1. And this will be just a set of mixed strategies for Pi. And we showed that a Nash equilibrium exists in this setting also. So basically, there exists a set of mixed strategies. So essentially, like so player 1 has a mixed strategy, player 2 has a mixed strategy, player 3 has a mixed strategy. So that all of these players together, when all of these players play these strategies, like player 1 plays the mixed strategy M1, player 2 plays the mixed strategy M2, and so on, then no player really wants to change his or her strategy. This is what we call the Nash equilibrium. So what was shown in the lectures was that Nash equilibrium exists in this kind of a game also. And how did we proceed to show that Nash equilibrium exists in this kind of a game? It was done basically using first what we did was for every mixed strategy we defined something as a set of best responses, and we defined a mapping. We defined that set of best responses as a mapping, and then we used. So I'm just giving a very high level idea. So basically, the high level idea essentially was just for every mixed strategy, just denote the set of best responses by a function capital R or a mapping capital R. And then we said that this mapping will have a fixed point, and it was done using this Kakutani's fixed point theorem. So this Kakutani's fixed point theorem was used to prove existence of Nash equilibrium of a non-zero sum game. So basically this game in a finite strategy space. And what was this Kakutani's fixed point theorem actually? So Kakutani's fixed point theorem is, note that this theorem is actually independent of this specific non-zero sum games or anything. This is a general theorem in mathematics. So it holds for it can be applied to any kind of setting, not just this strategies and everything, but otherwise also. And what does this Kakutani's fixed point theorem say? So if a set S, which is a subset of Rn, is convex closed and bounded. And suppose phi is a mapping from S to 2 to the S. 2 to the S is nothing but the power set of S, set of all possible subsets of S. So let phi be a set valued map. So for each set, we are mapping it to some subset of S. So what this phi function is essentially doing is it's mapping every element of S to some subset of S. So this is why we are calling it a set valued map. And then if we have these two conditions that phi is convex valued, which just means that phi of x is convex for all x belonging to x. So note that phi of x is, so for any element x, phi of x is just a subset, right? So the subset which we obtain, so phi of x is a subset of this set S, and S is essentially a subset of Rn. So phi of x is also a subset of Rn. So phi of x is a set of points in Rn. And now what we want really is that this set of points should be convex. And if this is true, then we say that phi is convex valued. So if phi is convex valued, and second condition is if phi has a closed graph. So closed graph was also so if phi has a closed graph and phi is convex valued, then what we can essentially say is that phi will admit a fixed point. This is what Kakutani's fixed point theorem essentially says. And what does this closed graph mean? So closed graph is nothing but you can think of it as when we call a set as closed. Similarly, now we are defining like the mapping this phi, mapping this phi to be closed. So if this mapping is closed, like essentially like phi of, if we take the set phi of x for all x belonging to S, then that set S should be closed. This is what we call as phi having a closed graph. So something like that. Then phi admits a fixed point. So this was Kakutani's fixed point theorem. And then how did we go about existence of? Okay, so I think Manas has joined the chat. So hello Manas. So we were just starting with the this session only, and in this session so I was, since this week's lectures were a lot more theoretical in nature, so I was just going through the high level ideas which were discussed in this week's lectures. I'm not doing really anything like anything new right now, or not discussing any problems, but rather just going through whatever was discussed to give a quick recap, because I believe like all of these proofs which were discussed can be a bit hard to assimilate if not done properly. So that's why I was, yeah. But note that this is not in any way a replacement to the lectures, because in a 2-hour session I can't really summarize and then give problems about like 1 week worth of lectures. So yeah, so I have just like copied some snippets from the lectures, some important bits which I felt were the most important. So essentially, first we defined what a non-zero sum game in a finite pure strategy space is, and this was the model which we assumed. And then what we really did was we then tried to prove that in this kind of a model non-zero sum game, whether a Nash we tried to prove that Nash equilibrium exists in this game also, in this kind of a game also. And for this, we use this Kakutani fixed point theorem, which was used to prove existence of Nash equilibrium of a non-zero sum game in a finite strategy space. And this was really the Kakutani's fixed point theorem. And the high level idea of how did we go about using this Kakutani's fixed point theorem was that for every mixed strategy profile for a player, we defined a function which we called the best response, that kind of function. And what we really showed was that this best response function actually follows the properties of this Kakutani's fixed point theorem, the two properties. And so essentially, the best response function admits some kind of a fixed point. And so what it essentially means is that the best response to a set of strategies is that strategy itself. This was something which we kind of did, and yeah. So this was the high level idea, that define an appropriate function which we called the best response function. Like what's the best response for some mixed strategy small yi, and then showed that this function essentially satisfies Kakutani's like conditions, and so it has a fixed point. And like fixed point just means that phi of x, like x should be a subset of phi of x, essentially saying that best response to something is to a strategy is that strategy itself. Okay, so Manas is typing something in the chat, I believe. So, so, so actually, Manas, that's what I'm trying to say. So what Manas is asking is if best response to best strategy by other players is that strategy itself. So note that in general, Manas, this is not true. Like this, you can't normally say that this will be true. But what we show is so that's why like if this was true, if what you're claiming is true, like then like every point will be a Nash equilibrium. But what we showed using Kakutani's fixed point theorem is that there will exist one set of strategies. So not every set of strategies satisfies this property that best response to best strategy is that strategy itself. But there will exist one set of strategies where like every player plays like some set strategy, like player one plays M1, player two plays M2, player three plays M3, such that the best response to M1, M2, M3, M4 till Mn minus 1 is the strategy Mn itself. So essentially, like what we showed was there exists a point. We did not discuss how to find the point or something. So Kagutani's fixed point theorem just says that there will be a fixed point. It's about existence. It's not about finding the strategy or anything, but there will exist something. Okay, so Manas is again typing something in the chat, I believe. No. So, okay, so Manas is saying that there exists one mixed strategy that is Nash equilibrium, but it means Nash equilibrium is unique. So note that Manas, we just said that there exists at least one fixed point. Like we did not say that the fixed point is unique or anything. It is not really unique. Like in many cases you can find that there will be more than one fixed points. But what we are saying is at least there will be one fixed point. So Nash equilibrium being unique is something like no, like we can't say that Nash equilibrium is unique. There can be multiple Nash equilibriums. Yeah. Yeah. So there can be many fixed points. So yes, good job, Manas. That's precisely what we are doing. Okay. So this was the high level idea for showing the like for a non-zero sum game in a finite pure strategy space, showing that there will be some Nash equilibrium. And then we went on to like in the next lectures, we went on to showing that Nash equilibrium exists in infinite strategy space also. Like if the set of, okay, so I should mention that first. So previously we assumed in this theorem that the set of pure strategies is finite. So a set of pure, the SI is the set of pure strategies for player I, and this set is finite. But now let's assume that there are infinite set of pure strategies also. So the number of pure strategies is also infinite. So that's where really so this kind of proof comes in. Here we use like Brouwer's fixed point theorem, which we'll come to late now. So what we now discuss is suppose like there is an infinite pure strategy space. The set of pure strategies is infinite. So now like this can be modeled as saying something as the set of pure strategies is actually a subset of like this set of SI is now infinite set. So we can say something like this set SI is some subset of, let's say, R to the MI. So this is an infinite set. So it is a subset of, let's say, some infinite set. So now note that the mixed strategies will be actually like, so mixed strategies are defined over pure strategies, right? And this pure strategy is itself an infinite set. So mixed strategies will be like even larger infinite set. like whatever that means. I'm not going to say what's larger or what's not larger, but here what essentially we were able to show, or like the theorem, this was not proved rigorously, but the theorem here is that Nash equilibrium exists also, but under certain assumptions. So suppose SI, this set of strategies for each player. So this is an infinite set. So suppose this set is convex, closed, and bounded. So what do we mean by a convex set? So by a convex set, we mean like if there are 2 points in the set, then any point lying between those, any linear combination of those 2 points should also lie in the set. So if SI is convex, closed, and bounded for each I, and the utility function, the utility function which we have over xi is continuous and strictly convex, then there exists a Nash equilibrium for the game. So there are some assumptions which we needed to place here, that SI should be convex, closed, and bounded, and then UI is continuous in xi, x minus I, and strictly convex in xi. And in this case, we were able to say that there will exist a Nash equilibrium for this game. Also, to add further, like actually, here we were able to show something much more interesting. So earlier, in this kind of a game, non-zero sum game in a finite pure strategy space, we showed that essentially a Nash equilibrium exists in terms of mixed strategies. Like it need not necessarily exist in terms of pure strategies, but in terms of mixed strategies, Nash equilibrium will always exist. But in this setting, when the pure strategy space is infinite, and these kinds of assumptions are followed, that strategy space is convex, closed, and bounded, and the payoff function is continuous in xi, x minus I, and strictly convex in xi, then actually, maybe I should add a note. Then actually there will also, like, there can be an Nash equilibrium in mixed strategies also, but there will also exist at least one Nash equilibrium in pure strategies. In the above setting, there exists a Nash equilibrium there even exists a Nash equilibrium where every player plays some. So it's a good theory question. Like it might come up in like not this week's quiz, or I don't know if it's in this week's quiz or something, but it can definitely come up in the exam, that like in this setting. So this was also shown in the lectures, that in this kind of a setting, if we have a size convex, closed, and bounded, and UI is continuous and strictly convex in xi, then there exists an Nash equilibrium. Like we don't even need the assumption of mixed strategies. Like we don't even need to talk about mixed strategies, but in terms of pure strategies also there will exist a Nash equilibrium. So this is a much stronger thing. So I hope you understand what I'm trying to say here, that we don't need mixed we don't even need mixed strategies here. We can just talk about pure strategies and still Nash equilibrium will exist. And I think like it's a very cool property to have. Yeah. Even if every player plays yeah, I think this is a better wording. In the setting, there is a Nash equilibrium, even if every player plays only some pure strategy. So yeah. And for showing this, essentially, again, we went on to something like the best response. We went back to the best response function to a like set x minus I. And then we said that since this UI function is strictly convex in xi, so for a fixed x minus I, there will be a unique minima for the set. So there will be a unique minima which achieves like the minimum value for this payoff. And because of this, we can say that for some given x minus I, there will be a unique xi, which will be the which we'll be playing. So the best response here won't be a set, but it will be a specific value. And then we have actually that now, since it is not a set, but it's a specific value, then we just need to define a mapping from S to S rather than like S to like 2 to the S or something. And this was essentially what Prober's fixed point theorem gave us, that if S is a subset of Rn, which is closed, convex, and bounded, and F is a mapping from S to S, and this is continuous, then there exists X star such that F of X star equals to X star. So here also the high level idea is essentially the same as the previous one, that we are showing that the best response to a set of strategies is the strategy which the player is currently playing. So this is what we are trying to show, that there exists a set of strategies so that for each player, the best response to the set of other player strategy is the strategy played by that player right now. And yeah, so here also basically this F which we are talking about is the best response function only. But here now this best response is mapped from S to S because the best response to some X minus I is unique because of this strictly convex assumption. And because of these assumptions that SI is convex, closed, and bounded, we are also able to obtain that S is convex, closed, and bounded. And we also are able to obtain that this F is continuous. So because of these conditions, there exists a fixed point for the best response function. And if there exists a fixed point for the best response function, then yeah, then that means that we have a Nash equilibrium. So yeah, exactly, Manas. So Manas is writing that basically we don't need probability space. That's correct. If the set of strategies is pure strategy is infinite, then like to find a Nash equilibrium, you don't even need the probability space. Like not to find, but for existence. What I mean is like existence of Nash equilibrium is like there exists at least one Nash equilibrium in the pure strategy space. Note that it does not imply that there won't exist any mixed strategy Nash equilibrium. So there might be some Nash equilibriums in the probability space also. But what I'm saying is there will also be a Nash equilibrium in the pure strategy space. Yeah. So I hope this point is clear. Okay, then. So these were the high level ideas which were used in like for proving like existence of Nash equilibriums, and after these we went on to this quantal response kind of a thing. So quantal response was saying something like, okay, what we have talked till now, like in terms of Nash equilibriums and everything, was the best response of a player. That what a player is doing is essentially the best response to what other players are doing. But note that, but then the motivation behind discussing this quantal response was, so in real world, like not every player is perfect, right? Like a player might not always play the best response to the other player's strategy because of nervousness, some external factor, or something. So we kind of want to model this fact that the player is not perfect and the player can play other strategies also. So now again we are talking about like the best strategy not being played, but rather there being a probability space over the set of pure strategies. So suppose like even if you have a pure strategy, which is the best response, but still the player will play a mixed strategy. Like player will play every strategy with some probability, and that's what we call something like the quantal response. What we're essentially saying is, suppose there are two strategies. One has a payoff of 2, other has a payoff of 5. So for a player, suppose I have a choice. I'm a player and I have two strategies. One has a payoff of 2, one has a payoff of 5. So what I'll do is my best response might be to play the strategy which gives me a payoff of 5, right? Because that's the best response. But another thing which I can do is, okay, maybe not the best response, but rather I try to have somewhat of a probability space because I'm not perfect. So maybe I'll say, okay, like this is 2, there's this 5. So maybe I'll try to say that with probability 2 by 7, I'll play the strategy which nets me a profit of 2. And with probability 5 by 7, I'll play the strategy which gives me a profit of 5. So essentially, I'll play these two strategies in terms of the ratios of profits which these give me. So I hope this makes sense that maybe as a player, I'll try to say that I'll play the strategies in the ratio of the profits which these strategies are giving me. Or I can give, or like, so this is what we call essentially quantal response. So quantal response is essentially saying that every strategy is played with some probabilities. So right, and so the best, so playing the best strategy is also a specific case of quantal response where the best strategy is played with the probability of one and other probability strategies are played with the probability zero. So quantal response is again talking about the probability spaces. And here the main thing is quantal response is not really that hard to understand. So yeah, quantal response says just that. So suppose the sigma ij is the notation that ith player is playing the pure strategy J. So the probability that the ith player plays the pure strategy J is nothing but equal to Vij divided by summation Vij prime over J prime over RSI. So what this essentially means is suppose so what this Vij denotes is just so this Vij is nothing but uh, the weightage over the reward functions. So suppose there are some payoffs of on playing strategy J1, J2, J3, and so on. So then Vij is nothing but it defines how much importance do we want to give to each of these rewards. Like if one strategy nets me a reward of 2 and other strategy gives me a reward of 5, then how much weightage should I give the strategy 2 and how much should I give 5? Like the best case response would say that okay, the strategy which gives me a payoff of 5 is the most important and give all of its weight to that strategy. But the other strategy might be give a 2 by 7 weight to the strategy 2 and 5 by 7 to the strategy which gives me 5. And in general, this was discussed in the lectures that one can give 2 raised to the power lambda to the strategy which gives me a payoff of 2 and 5 to the lambda to the strategy which gives me a payoff of 5. And this lambda is called the responsiveness of the quantal response function and something like that. So yeah, so minus, yeah, so similar to softmax kind of operation, bringing down to 0, 1. So yeah, minus, anyways, we are talking about probabilities. So we'll need the probabilities to be in 0 to 1 space, right? Because probabilities can't be greater. So this Vij is not 0 to 1. Note that this Vij can be greater also. So this Vij, you can think of it as just a mapping from payoffs to how each strategy is giving me some payoff and how much importance do I want to give to that strategy. So this is what Vij is giving to me. And I'm just taking the ratios of these importances in this kind of function because in the end I want some probabilities, right? So this is the high level idea, but we'll solve we'll try to solve maybe 1 or 2 problems related to this so that this becomes a bit clearer. Okay, and then again, it's not really hard to show that okay, one might say that if we form these kinds of equations, how are we so sure that we will be able to obtain a solution to these equations? Like not every set of equations has a solution, right? Like in reals, suppose I want to say that x square equal to minus 1, then it does not have a solution in reals. So these sets of equations, why will these have a solution? So then this was discussed also in 1 or 2 lines that again you can show that the set of quantal responses will have a fixed point, and so you can show that quantal response also always exists. So yeah. So again, you can earlier we were talking about Nash equilibrium and Nash equilibrium exists. So now quantal response equilibrium also actually exists. And yeah, using fixed points, you can show that quantal response equilibrium exists. So Manas is typing something in the chat. Okay. So Manas is saying, what if one player has only one pure strategy? That will be constraint on that player, not a strategy. What do you mean by this, Manas? Sorry, I did not get this. So if one player has pure strategy, I understand. So what? Oh, so Manas is just pointing out that with respect to the other player, what might happen is if the second player has only one strategy, now I have to be constrained in giving my responses. That's what you're saying, right? Ah, oh, that's a good insight. Yeah, that makes sense. Um, that if I have, so one player has only one strategy, then the other player has to like other player has many options to play some strategies, but now those set of strategies which the player can play is now restricted because the first player has only one strategy. So you can visualize being constrained, some of the constraints as just one of the players having just one strategy. This makes sense. Nice. Thanks for the insight. Okay, then if we are, I think if we are clear with the like at least the high level ideas or whatever was discussed in this week, the theory which was discussed, then maybe we can move to some of the problem statements. So the problems, since the lectures were theoretical in nature, the problems will also be tend to be like more theoretical rather than numerical this time around. Yeah, but there are one or two numericals also, I believe, at the end. So let's start with the first question then. So let Ri y minus I be the best response of a player I for a strategy for an opponent strategy y minus I. So essentially what we are saying is if the uh, with respect to player I, if all other players play some strategy y minus I, then we are defining this Ri y minus I to be the best response function. So best response is nothing but yi is like the yi is so Ri y minus I is just the set of those strategies yi's which are essentially best strategies. And this is like in terms of mixed strategies we are talking. So this is just the like basic definition for the best response. So like what this is saying is the strategy yi. So this ry of y minus I is just those strategies yi's such that the payoff on playing yi is always less than equal to the payoff on playing any other strategy y. Right? Since we are trying to minimize our payoffs, so the best strategy will be the one from for which uh, with respect to every other player strategy, the payoff is minimum. So this is just the definition we discussed in the lectures also, the best response set. Now the problem, there are two statements. The statement A says that the set Ri y minus I is a convex set. And statement B is if y star is a Nash equilibrium, then y star of I is a subset of Ri of y star of minus I for all I. So which of these is a correct statement? So would you like to answer this, Manav? Okay, also assume, maybe you can just assume. Uh, I don't think it matters, but okay, let's not write it. It doesn't matter. Yeah. So the answer should be A. So yeah, that statement A is true and B is true. So yeah, that's actually correct, Manas. So maybe I'll just discuss this also. So we can discuss it statement by statement. So statement A says that the set Ri y minus I is a convex set for all I. So note that this Ri y minus I was precisely the set which we took in this in proving that non-zero sum game has a Nash equilibrium. Here we applied like Kakutani's 6-point theorem to this set only, the Ri minus I1, the mapping of this kind. And here we actually showed in one of the lectures that this is convex value. So yeah, this was again straight from lectures, but just keeping in mind what all have we discussed in the lectures. So yeah, so Ri of y minus I is convex valued. What was it exactly what we used? So this is a convex set, which we showed in the proving also. And note that it's also not too hard to see also, like, why will this be a convex set? Like, yeah. And then the second statement is if y star is, so maybe I'll just say that statement A is true, as discussed in the lectures, right? And now statement B is if y star is a Nash equilibrium, then y star of I is a subset of Ri of y star of minus I. So what this essentially is saying is the best response. So suppose y star is a Nash equilibrium, then what we mean is if I consider all set of all like the response, basically the strategies played by everyone except the player I. Except the player I, if I consider the strategies played by other players, then the best response to those strategies is the strategy played by the ith player itself. Like, so basically, the strategy played by the ith player itself should be a subset of, should be a one of the best. It might not be the unique best response, but it should be one of the best responses in a Nash equilibrium. And this should hold true for all I. And this is only when like no player will have an incentive to switch to a different strategy, right? And this is precisely the high level intuition of a Nash equilibrium, that no player has an incentive to switch to another strategy. And if the strategy played by a player is the best response to the other strategies, then the player will really not have much incentive to switch. So yeah, so this is just from the basic definition of Nash equilibrium. Yeah, statement B is true from the definition of Nash equilibrium. So yeah, so hence option is correct. Just try that. Right. Okay, then maybe we can move on to the second question. So second question is again like true false only. So let R be a function from the space of strategies to power set, where like Ri y minus I is the best response for a strategy y minus I. So again, like we just take the best response function for each of the players and take the cross product of these, and this is what we call the Ry function. So note that now each of these best responses is a set of strategies. So now this is a set of sets. Uh, yeah, so this R of y is nothing but basically like a function in like 2 to the y space. Like this is again like really easy to see. And now consider the following statements: that the mapping R is convex valued, the mapping R has a closed graph. So again, actually, so I think this is just more or less similar to the previous question itself. Like this was, so earlier I said that in the lectures we showed that Ri y minus I is a best, like this best response function for each player is like convex valued and everything, is a convex set and everything. And like from this, like in the lectures also we concluded that if each of these is convex valued, then like this whole term is also convex valued. So actually mapping R is convex valued, and like this function R was precisely the function which we showed using Kakutani's fixed point theorem, that this is the precise function which will have a fixed point. So this was the function which we said that is having a fixed point. And yeah, so and the conditions for Kakutani's fixed point theorem were these itself, that the mapping should be convex valued and the mapping should have a closed graph. We can just remind ourselves that phi has a closed graph, so R should have a closed graph and R should be convex valued. And we showed both of these properties in the lectures. That's why this R was precisely the function which we took as phi, and we showed that it admits a fixed point. So yeah, so both are actually true. So again, good job, Manas, that both are true. Or maybe I'll just write this down. Both the statements are true as discussed in the lectures. Yeah. Maybe just as a note, I can write these are precisely the conditions we need to show to apply time. fixed point theorem 2. Yeah. Okay, so Manas is saying that maybe we can use some different notation to represent Cartesian product of set, not the same as multiply. Uh, isn't usually okay. Yes, Manas. So yeah, like it is obvious that Cartesian product of convex set is convex. So yeah, but usually isn't Cartesian product actually usually represent? I believe usually like Cartesian product is represented as multiply only, like using this multiplication symbol only, like because if one really know, like if it is clear that I think it's a standard notation that a set multiply, like if there's a multiplication symbol between two sets, then we are just talking about Cartesian products. Ah, yeah, like it would be much like it could be nice if we use something different also, but I think this is just like obviously you can define a different symbol. I don't know, maybe multiply underscore s or something, some other symbol, and just say that that symbol denotes the Cartesian product. Or like if we are just following the standard notation, then just by seeing this cross and these sets, everyone will understand by themselves that this is a Cartesian product. Hmm. But yeah, I think what you're saying definitely makes sense. Like it might decrease the confusion, but I think if one is clear with if these are sets, then like just using a cross this multiply as a Cartesian product is also fine. Nevertheless, maybe we can like move on to the third question. Again, like as I said, that these are theoretical questions only, more or less. So consider the following statements about the quantal response function. So first statement is as the responsiveness of the quantal response function tends to zero, the quantal response gives uniform probability to all strategies. Statement B is as the responsiveness tends to infinity, the function gives the best response strategy. Okay, it might reinforce to think in terms of set. Okay, maybe yeah, maybe I'll just denote I think just maybe I can just write down this. Yeah, and this would. But yeah, maybe we can move on to this third question then. Uh, so this was also basically covered in the lectures itself that the responsiveness is the parameter lambda, which I was really talking about. Uh, that in the quantal response function, what we have is like a Vij to the power. So we have something like a Vij divided by sigma Vij, and yeah. Okay, sorry for this, guys. Yeah. But we can also have something like Vij to the lambda divided by summation of Vij's to the lambdas. And that's essentially the responsiveness. And this was discussed in the lecture also that if the responsiveness is, so if the response, so if lambda is actually zero, as lambda tends to zero, So note that in general in quantum response, so this is where this was just the quantum response if we assume that we are just doing it everything in terms of like ratios of Vij's. But actually, like if we have a general lambda also, then the quantum response is actually equal to Vij raised to the lambda divided by some of these Vij's raised to the lambdas. So what we have is Vij raised to the lambda divided by Vij prime raised to the lambda and summed over all SIs. So as lambda tends to 0, all of these things like the Vij raised to the 0 will become 1. And similarly in denominator also we'll have summation of ones. So what we'll essentially get is every strategy is being played with a constant probability and equal, like those will be equal also. So that's how we get that every strategy is played with like uniform probabilities. And as lambda tends to infinity, you'll see that only the best strategy is played with probability 1 and other strategies are played with probability 0. And that's how we get that as the responsiveness tends to infinity, uh, the function gives the best response strategy. Because as lambda tends to infinity, we'll give best response. And like here we saw that every strategy will have unique probability. So again, like both the statements are true as discussed in the lectures. So yeah. Okay, then again, after this, maybe we can move on to the fourth question. Okay, I think Manas has dropped out, so I'll be again addressing the YouTube audience only. So let y1, y1k, y2k, yn k be a sequence of strategies that converges to y equals to y1 to yn. So like suppose this y1 comma. So what we have is like there are n players. So player 1 is playing the strategy y1, player 2 is playing the strategy y2, player n is playing the strategy yn, and like all of these underscore k's. And what this essentially means is like this, consider this an n-dimensional vector, and you are having a sequence of this n-dimensional vector. Like k will be going from like let's say 1 to infinity or something. So we'll have really y1 1, y2 1, y3 1. This will be one sequence till yn1 when k is 1. And when k is 2, we'll have a sequence, like we'll have a vector which has entries y1 2, y2 2 till yn2. So basically we are having a infinite sequence of these n-dimensional vectors. So we have a sequence of strategies essentially. Like these are n objects. Like these in itself can be vectors. These y's can itself be vectors. But yeah, for now, like we can just say that this n size collections we'll be having this sequence of these n size collections here. And this each of these collection corresponds to some strategies, right? So like this corresponds to like the player 1 playing the strategy y1k and similarly player n playing the strategy yn-k. And if this and if all of this converges to, let's say, this sequence of strategies converges to something like y1 till yn, that if you take the limit k tends to infinity in this, then it's equal to actually y1 to yn. So suppose like this is true that if we take a sequence and it in its limit it goes to y1 to yn, then the problem asks if for some I, yik is a subset of the best. So Ri is again the best response set. So yik is nothing but so yik is just the yikth element in the sequence. And if this is a subset of like r y minus ik, so basically if yik is the best response to the strategies y1k, y2k till yi minus k, and then yi plus 1k till ynk. So in this sequence, so in this set of strategies, if yik is the best response to the other strategies, and if this holds true for all k, then yi is also a best response to. So essentially what we are saying is if this best response property is satisfied for each of these set of strategies in the sequence, and and this holds true like for like yeah, for some specific I, if this holds true for like for all values of k, then as we go to like infinity in the limit, yi is essentially the best response to y minus I. So is this statement true or false? So I think this kind of got a bit confusing, but let me just state it again. So what we're essentially saying is, suppose we fix some I, and we say for that fixed I, like yik will be the best response to all other strategies for all k. So we are talking about some fixed I, but we are saying that that I is always giving the best response for all of these elements in the sequence. Then yi will be a best response to like in the limit also. So note that this is like objectively true, because if this is true for all sequences, then in the limit also this will be true, because everything is converging, and this is from like basic properties only. Like yeah, actually like what you essentially are showing, what essentially this is talking about is the fact that the set R is closed. Like if you want to show that the best response function is closed, which we really needed to show for the Kakutani's fixed point theorem, then this is the property which you need to show for being closed. And yeah, this will be like easily true. Like this was discussed in the lectures also. And the intuition to this is this itself, that in the limit, like you can argue that this thing will be always better than the others. So yeah. So this is also actually true, and this was also discussed in the lectures. And the proof for this, as which was discussed in the lectures, was something like this only, that like yik is the best response to yi minus k. So we set up some inequality. We say that yik is less than so basically the reward on playing yik is less than equal to playing some any other strategy yi prime k. And then if we take the limit, then we can say that yi is the best response strategy uh, with respect to any, like, is a better strategy than any yi prime in the limit also. And from that we can obtain this. So again, this is true as discussed in the lectures. Okay, like I hope this made a bit of sense. The proof for this property was again in the lectures, and yeah, the idea for showing this was that consider some other strategy y prime on yi prime, and then you can say that yik will be less, the payoff on playing yik will be less than equal to the payoff on playing yi prime k, and this will hold true for all k. So then you can actually say that like the payoff on playing yi will be better than payoff on playing yi prime. And yi prime was arbitrary, so you can choose yi prime as anything. And so you will actually get that for all strategies, yi will be the best one, essentially. So yeah. So just giving the high level descriptions because everything was already covered in the lectures. So yeah. Now we get to some not exactly a very difficult question, but still a new question nonetheless, not a theoretical one. So consider the game of matching pennies, where the P1 is the row player and P2 is the column player, and both players are trying to maximize their utility. So here what we have is the payoff matrices for the two players. The first entry of each of these payoff matrices denotes the payoff for the row player, and second entry denotes the payoff for the column player. So now if we have that y square, y2 is 0.5, 0.5, and note that this y square is like I hope everyone understands the notation, that this y square doesn't, this notation was also discussed in the lectures only. This is not y square. This is essentially the strategy played by the player two, similar to the notations where we had, which we had the here also. Like here, this was strategy by player one, strategy by player n. Clearly strategy by player 1, strategy by player n. Similarly here, this is the strategy played by player 2. So suppose player 2 plays the strategy. So player 2 is the column player 1 is the row player. So player 2 plays a strategy of 0.5, 0.5, which means that column player is playing heads with probability 0.5 and tails with probability 0.5. Okay. Then what we want is the best. So R1 of y square is nothing but the best response set with respect to this strategy of player 2. So if player 2 is playing the strategy 0.5, 0.5, then what will be R is the best response function, right? So what will be the best response by the player 1 to this kind of a strategy? So maybe I should write this also. So we can see that R1 y square corresponds to the best response set of player 1 when player 2 plays the strategy 0.5, 0. Okay. So this will be the best response set. So this will be a set of points. So note that R1 square will be a set of points in 2D space, right? R1 of R1 of y2 will be a set of points like where the each set of points will be like of the form x comma y, where like x will the probability of playing heads and t will be the probability of playing tails. Let's say x comma y, where x is the probability of playing heads and y is the probability of playing tails. So x comma y will be the uh, strategy for like yeah. So that's why it's a subset in 0, 1 squared, because like one needs to say that like for x comma y, like so there will be set of points x comma y's which will be, or maybe like x comma y will be a bit confusing. There's a set of points a comma b, which will the set of points a comma b which will be like best responses to this. And now we have to find the area of this, like R1 of y square. So we have to essentially like we have this set of points and this set of points will somewhat make a closed curve. And now we have to find the area of a curve. Right. So this is essentially the problem. So what we have is a consider. So what can we do here is like, actually the problem is quite simple. Like consider a comma b, and like let's say a comma b is a subset of R1 of y square. So what this essentially means is like if a comma b is a subset of y square, R1 of y square, then what this means is like for any other a prime comma b prime or any other mixed strategy of player 1, strategy a prime b player 1, we have that like payoff on playing a, and like the column player is just doing half for both of these. It is given to us that column player is doing half for both of these. So payoff for this player will be like if the column player is playing half with here, then the row player will have a probability of so basically the chance of head comma head occurring will be something like a by 2, because row player is doing it with probability a, row player is playing heads with probability a, and column player is playing it with probability half. So this will be 1. Here the row player is earning a payoff of 1. But here the row, and in these two cases, row player is playing earning a payoff of 0. So maybe I'll just put this. So yeah. So b into 1 by 2 into 0. So this is like row player playing tails, but column player still playing heads. So this will be a payoff of 0. Similarly, row player playing heads, but column player playing tails will be something like, again, a times half times 0, because row player's payoff is again 0. And if both are playing tails, this occurs with probability of uh, b times half times 1, right? So this is the payoff for the row player. And this should be less than equal to like payoff on playing a prime b prime should be like payoff less than equal to payoff on playing like greater than equal to payoff on playing a comma b. So what this implies is, yeah, okay, so this is a prime b prime a prime b prime. Yeah, now it's better. So this should be the inequality which should follow for like a comma b to be in the best response set to 0.5 comma 0.5. And but what this essentially means is like what we'll essentially see is actually this is trivial. So now let's see that. So this is a 0, so this is a 0, so these will get ignored. But now the remaining sum is a by 2 plus b by 2. So the remaining sum will be equal to a plus b by 2. And similarly, in this side, the sum will be something like a prime plus b prime divided by 2. But note that a comma b and a prime comma b prime are like there is also a constraint that a plus b and a prime plus b prime should all be equal to 1, because sum of probabilities over all strategies should be equal to 1. So here we'll get a 1, here we'll get a 1, so we'll get that half is less than equal to half, which is trivially true. Since a plus b is equals to 1 is equals to a prime plus b prime, hence the above inequality holds true trivially. And so this actually holds for any a comma b. So if you take any a comma b, you really don't have any constraints on a comma b. The only constraints being a is greater than equal to 0, b is greater than equal to 0, and a plus b less than equal to 1. Because like this is the probability set, right? So the above inequality holds true trivially. The only condition being that this set of the set of points should be like forming a probability distributions. So hence all a comma b such that a is greater than equal to 0, or maybe like hence all valid a comma b are part of, maybe I should like something like say, are part of R1 of y square, like R1 of y2. So if 0.5 comma 0.5 is placed, then any valid strategy, like any probability which the player any probability distribution by any valid probability distribution of player 1 will be a valid response. Like it will be in the best response to like the strategy 0.5 comma 0.5. So what this essentially means is if player 2 is playing 0.5 comma 0.5, I can play any response, any mixed strategy, and it will be a valid strategy. So essentially what this means is R1 of y square is nothing but the all set of all valid probability points, right? R1 of y2 is nothing but the set of points a comma b such that they form a, the only constraint is like there is no constraint of payoffs now because we see that this best response constraint is trivial for any a comma b. The only constraints which we have is like now a greater than equal to 0, b greater than equal to 0, and a plus b being equal to 1. So yeah. Okay, I think there's some issue here, guys. So R1 of y square is nothing but the R1 of y2 is nothing but the best response by player 1 when this player is playing 0.5, 0.5. So player 1 can play anything and it will be a valid response, right? And now what we want is so basically any set of so n R1 of y square will be a subset of 0 to 1 squared because like this will just be a set of points in the 2D space. R1 of y square will be a set of points. Okay, maybe I should yeah. Now it's much simpler. So yeah. So the question now asks us so what we have is the set of points a comma b such that a is greater than equal to 0, b is greater than equal to 0, and a plus b is equal to 1. Right? And so what is these are the set of points which will be valid for me. Okay, maybe yeah. I think this kind of a definition makes sense. Okay, maybe we should just focus on this. So note that so the only constraint which we really need is like so the you can see what the straight line a plus b equal to 1 will look like. So r1 y square is just so a plus b equal to 1 will be a straight line in the 2D plane, right? So a plus b, consider a as the x coordinate and b as the y coordinate. Then a plus b equal to 1 is just a straight line. And it should be like and since a is greater than equal to b 0 and b is greater than equal to 0, this straight line should just be going from the points 1 comma 0. So it will just be a line segment which will start from 1 comma 0 and end at 0 comma 1. So hence r1 of y square, okay, r1 of y2 is a line segment starting from 0 comma 1 and ending at 1 comma 0. Okay, maybe I should, yeah. So now, yeah, so we know that this is a line segment. So the r1 y square is a set of points, but this is just a line segment. Like it's a set of points which start from 0 comma 1 to 1 comma 0. But it's really just a line segment and nothing else. And now, yeah, you can't really okay. And now you can't really like find an area of a line segment, right? Like uh one can't like one can't find an area of a line segment. But like what you can find is like the area of the curve which will be formed by this line segment. So the closed curve of this line segment with x and y axis. So note that x plus y equal to 1 will be one of the line segments and x and y will be two more sides. So basically this will form a triangle. So one side of the triangle will be this line segment which goes from 0, 1 and 1, 0, and the other sides will be the x-axis and the y-axis. So hence R1 of y2 forms a triangle of uh, high triangle, forms a right angle triangle. I think you can understand the picture yourself, guys, because like a plus b equal to 1 and a greater than equal to 0 and b greater than equal to 0. Like this will be a closed curve, like x-axis, y-axis, and this line a plus b equal to 1. And this will be a triangle which will be like having a height of 1 and a base of 1, and this will be a right angle triangle. Height equal to 1 and base equal to 1. Hence, area of this triangle is equals to half into base into height. So area of this right angle triangle will be just half into base into height. So this will be 1 by 2 into 1 into 1, which will be 0.5. So yeah, so this will really be the fine answer for us. Like, okay, so the question was a bit convoluted. I think initially the question was a bit confusing, like because there will be no like the set of points which are forming R1 y square is a line segment and not uh, a closed figure. So essentially, like claiming the area of a line segment, then you will just have to say that the area of a line segment is 0, right? Area of a line segment is 0, like it's a one-dimensional figure. But then, like, if I had to still maintain the question, like, what I meant by the area was that area of the closed curve, which was formed by R1 y square with x and y axis. So now it's a triangle because like x and y axis are the two sides of the triangle. And now it's really a closed curve and its area is like half into 1 into 1, which will be 0.5. So this will be the answer. So sorry for the confusion, guys. Like, yeah, the answer would be 0.5. Yeah. Okay, then maybe we can move on to the sixth question. So sixth question says that consider the following statements about the quantal response function. And the statement A says that consider any two pure strategies. Then the probability of playing the strategy with the higher expected utility is higher than the probability of playing the strategy with the lower expected utility. So again, this statement was discussed in the lectures, and yeah, this statement is true. Like what you usually want is the probability in the probability distribution of quantum responses in such a way that the higher utilities payoff should be like the higher payoffs should have like higher probabilities and lower payoffs should have lower probabilities, something like that. We are assuming everyone is trying to maximize their payoffs, that is. So statement is actually correct as discussed in the lectures. Statement A. Correct as discussed in the lectures. And what about statement B? So note that statement B is quantum response equilibrium is also a Nash equilibrium. Note that like this is actually not correct because we have seen an example like if lambda, the lambda in the quantum response is the responsiveness. If we put the responsiveness equal to 0, lambda equal to 0, then actually what we get is a uniform distribution over all probabilities in the quantum response equilibrium. But note that uniform strategies is not necessarily a Nash equilibrium. Like you can easily construct examples where like uniform distribution is not a Nash equilibrium. So yeah, so this actually statement is false. Incorrect. For example, if responsiveness is equal to 0, then the each player lays a uniformly random strategy, which is not always, which is not necessarily a Nash equilibrium. But note that if lambda is infinity, so suppose if lambda tends to infinity, then we know that every player plays the best response strategy. This was also what was discussed. And then it actually corresponds to Nash equilibrium because best response strategy. So yeah, best response strategy is a Nash equilibrium. In general, quantal response equilibrium is not Nash equilibrium, but if lambda tends to infinity, then we can say that it is Nash equilibrium. Then quantal response equilibrium. Or will it? Okay. 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 I think like I would not like to comment on this. Maybe I think it won't be. Okay. Let's leave it like that. Yeah. So if each player plays a uniformly random strategy, it is not necessarily a Nash equilibrium. Yeah. But if lambda tends to infinity, it will be a best response equilibrium kind of a thing, which is actually Nash equilibrium. But let's not write it now. Okay. So statement A is true, B is false. So option B is correct. And option B is correct. Okay, then. Now maybe like, okay, so yeah. Now this is the seventh question, and now maybe we can discuss a numerical kind of a question for the quantum response equilibrium. So this is a numerical for the quantum response equilibrium, and its formula was already discussed in the lectures, but maybe we can just go through how everything was derived. So we are given in asymmetric matching pennies game where head gives row player as X. So first entry is again the payoff for the row player, second entry is the payoff for the column player. And in each element, X and Y are the utilities of P1 and P2 respectively. Each player is trying to maximize the utility. And now we want to find the quantal response equilibrium if the quantal response function is given as something like this. So we are given that this will be the quantal response equilibrium for us. So lambda actually, so note that VIJs have a coefficient of lambdas in general in quantal response equilibrium. But here we are assuming that lambdas is equal to 1. So note that the direct formula for this was also written in the lectures, like in this asymmetric matching pennies game, if sigma ij is something whatever this kind, what will be the solution? But we'll try to derive the solution ourselves so that we are a bit more comfortable with quantal response equilibrium. Note that it's not really difficult and it's quite easy. Like you'll also see why is it. So sigma ij is the probability with which player I plays strategy J. Vij is the utility of player I for strategy J. Si is the strategy space for player I. So these are just notations which we are talking about. So what will be the strategies of P1 and P2 in the quantal response equilibrium? So we need to find out the strategies. So again, let's just denote this sigma 1, sigma. So we are given these sigma ij's already, right? Like sigma ij denotes player I playing a strategy J. So there are I'll call heads as strategy 1 and tails as strategy 2. So convention will be we will refer to heads as strategy 1 and tails as strategy 2 for both players. So what this essentially means is sigma 1 will denote the strategy of uh, like sigma 1 will denote the strategy of player 1 playing the strategy 1, which is heads, and something like similar to that everything else. So maybe we can write down the equations. Yeah, maybe we can just write down the equation there. So what we have is sigma 1 So what is sigma 1? Sigma 1 is the probability that player 1 is playing the strategy 1. And what will this be equal to? So note that if player 1 is playing the strategy 1, so player 1 has two choices, playing strategy 1 or playing strategy 2. Player 1 is a role player. So if player 1 plays the strategy 1, what will be the payoff for the player 1? Let's see here. So if the column player is playing this strategy, if column player is also playing the strategy 1, then player 1 gets a payoff of x. So maybe we should just write it in terms of fractions because, yeah. So in the numerator, we'll have this Vij of sigma inverse, right? So the player 2 is right now, let's say, playing the strategy heads only. So basically, the player 2 will play the strategy heads with probability sigma 2 1, right? Like, because player 2 playing a strategy 1. And the payoff in this case is x for me. If player 1 plays the strategy 1. But if player 2 now plays, let's say, the strategy T, so let's say the player 2 plays the strategy T, and so player 2 plays this strategy with probability sigma 2 2, right? In this case, the payoff of player 1 will be 0, right? Because I should write it here, right? Yeah. So this will be the payoff if the player. So player 1 is, we are saying that player 1 is playing the strategy 1 only. And now we are saying like, we are seeing with what probability should the player actually be playing the strategy 1. So if player 1 plays the strategy 1, then what's the expected? So what we are essentially looking at is player 1 playing the strategy 1. What is the payoff for the player 1 in expectation? So player 1's payoff in expectation will be this kind of a quantity, right? X times sigma 2 1 plus 0 times sigma 2 2, and we'll have to divide it by some normalizing factor, which will be like summation over all sigma. So player 1 has two strategies, playing sigma 1 1 or playing sigma or playing strategy 2. So on playing strategy 1, the payoff is essentially this only. So we can just copy paste this. And on playing strategy 2, if player 1 plays the strategy 2, what will be the payoff for player 1? If player 1 is playing the strategy 2, if player 1 is playing tails, then the payoff will be 0 if the player 2 is playing strategy 1. So it will be sigma if player 2 plays the strategy 1, then the payoff will be this. Plus, if the player 2 plays the strategy 2 in this case, then it will be something like this. So it will be 1, that will be a payoff of 1. So it will be 1 times sigma 2. So note that this is the part which is coming from player 1 playing the strategy 2, the expected payoff when player 1 plays the strategy 2. This is the expected payoff when player 1 plays the strategy 1. And so like this is the probability with which sigma player 1 plays the strategy 1, right? And now similar equations we can form. So like we just form this equation. Similarly, we can form this one also, that like player 1 playing the strategy 2 was just this expression, right? The payoff on playing strategy 2 was this expression, and the denominator is just the normalizing function, so it remains the same. So we have these two equations, and similarly we'll have further equations which can be written in the form. So we have written the equations for like player 1, and now we'll write the equations for player 2. So if player 2, okay, maybe I should zoom out a little so that everyone can see. Yeah. So if player 2 plays a strategy 1, so now player 2 is the column player. So if player 2 plays the strategy 1, what are the payoff for the player 2? So if the row player plays the strategy 1, then player 2 is getting a payoff of 0. So player 2's payoff is 0. If the player 1 plays the strategy 1. right? So I'll be rewriting these like I'm just I've copied the expression and I'll be making appropriate changes to the expression. But if player one, okay, and now, but if player one plays the strategy two instead, we are talking about payoff for the player two right now when playing a strategy one. So we are looking at this column, the heads column, and we are saying that the row player, if it played heads, then the payoff was 0. But now if the row player played tails, then the payoff is 1 for the column player. So the payoff is 1 for player 2 when player 1 is playing the strategy 2. So if the row player is playing second strategy, the payoff is 1. So I'll make this appropriate change here also. So it will be something like, okay, yeah. I'll just copy this. Yeah, I'll paste it. So this will be really the uh, payoff on playing like strategy 1. And now let's see what's the payoff, expected payoff for player 2 on playing strategy 2. So if player 2 plays strategy 2, then the payoff is 1 if the row player plays strategy 1. So payoff is 1 if the row player plays strategy 1. And payoff is 0. Maybe I should, yeah, for appropriate. And payoff is 0 if the row player plays the strategy 2. Because if row player plays the strategy 2, then the payoff for the column player is 0. Something like this. And now maybe we have this kind of a thing here also. And now we have the sigma 2 and sigma 2 will have the payoff of these kind. Okay, so now we have these 4 equations. And it's easy to see that sigma 1 plus sigma 2 is equal to 0, is equal to 1. Similarly, sigma 1 plus sigma 2 is also equal to 1. So essentially so there are so you can essentially replace sigma 1 by sigma 2 by 1 minus sigma 1. And similarly, sigma 1 by 1 minus sigma 2. Okay, maybe we should just okay. Then maybe these are a set of equations. Quantal response equilibrium is given by the equations. The quantal response is given by this set of equations, and now we'll have to solve these equations. So first, let's just simplify these. Like maybe just write these in a better form. So note that sigma 1 plus sigma 2 is equal to 1 actually. So we can actually say that. Is there some network issues? I don't know what happened here. And I don't know what just crashed over. Yeah. Okay, it's nice. Nothing crashed. That's good. So we know that sigma 1 plus sigma 2 is 1. And similarly, sigma 2, because sum of probability should be equal to 1, right? So similarly, sigma 1 plus sigma 2 will also be equal to 1. So yeah. So yeah. Substituting these. Following equation. So now let's say these are equal to 1. So what I'm saying is I'll substitute sigma 2 as 1 minus sigma 1 in this kind of equation. And similarly, I'll substitute sigma 2 as 1 minus sigma 1 in this equation. So then we'll have 2 equations and 2 variables. Maybe I'll just copy the equation and show the first substitution myself. So maybe I'll just simplify also. So x times sigma 1 plus 0 times this will become a 0 itself. Similarly, I just remove all the terms which are adding zeros. and like one time something is also clear. So this is the equation which we had for sigma 1, 1, right? And sigma 2, 2, I'll just replace it by 1 minus sigma 2, 1. And now I'll also like do I'll do this equation also. I'll rewrite this equation also. So I'll say that this zero term I'll just remove. This one also I'll remove. And then here, this zero I'll remove. This one I'll remove. Just to simplify the equation. Okay. And then this zero can be fully removed. Yeah. And now sigma 1, 2 plus sigma 1, 1. We know this is equal to 1. So I just remove this also. Because like this is just equal to 1. Like this whole quantity sigma 1, 2 plus sigma 1, 1 is equal to 1, you know. So this can be replaced by 1 and like I'll just denote it by it's like without the fraction. I'll denote it without the fraction. So sigma 1. So only sigma 1, 2 remains here. So only sigma 1, 2 remains here. So if we have sigma 1, 2 equal to sigma 2, 1, and both of these were actually equal to half, both of these sums were equal to 1. So this means that both of these will be actually equal to half. Okay. So substituting this back into this, substituting like sigma 2, 1 and sigma everything as half, what we get is okay. Hence we get that. Maybe I'll just copy this equation and I'll just say that this is half. So this will be like this sigma 2, 1 is nothing but a half. But maybe I'll just okay. Something. Yeah. So like what I'm doing is I'm multiplying both numerator and denominator by 2 so that like the numerator as half becomes a 1 and similarly here also this half will become a 1. And why I'm doing this will become a bit clear. So this just becomes an x. And now this was 1 minus sigma 2 and this was also half. So this also became a 1. So I can just remove this and just write it as 1. So I'll get that sigma 1, 1 is x upon x plus 1. And similarly, I'll get sigma 2, 1 is equals to like sigma 2, 1 is nothing but sigma 1, 2 is nothing but 1 minus sigma 1, 1. So it will be, maybe I should just copy this. Yeah, sigma 1, 2 will be nothing but 1 minus this quantity. So you can calculate that it will come out to be 1 by x plus 1. So what we get is actually in the equilibrium like sigma 1, 1 will be x by x plus 1. This will be 1 by x plus 1. And these two will be equal to half. So this will be my final answer. Like hence, maybe I should not have bold, but layer 1 lays heads with probability x by x plus 1 and layer 2 lays heads with probability half. And note that playing tails will just be equal to 1 minus these probabilities. And this is my final answer. Like this is the uh, quantal response equilibrium. So hence in the quantal response Equilibrium. Player 1 plays heads with probability x by x plus 1, and player 2 plays heads with probability half. So this is my final answer for this question. So this was already discussed in the lectures, also the direct formula, but I just wanted to show you guys like how this formula comes about to give a better intuition about the quantum response equilibrium. Yeah. So if we are done with this, then maybe we can move on with the last question for the day. It's again a theory question, so it will be not too much if you have gone through the lectures. This says that consider the following statements about the quantum response function. So quantum response function gives a mixed strategy for a player. So we know that this gives a mixed strategy because like, yeah, it's a probability distribution over the set of pure strategies. And quantum response strategy gives zero probability to the dominated strategies. So note that this is incorrect. Like the statement B is incorrect because even if a strategy is dominated, what we do is we give some non-zero probability to every strategy, right? Like if a strategy gives me strictly like only a payoff of 5, but other gives a payoff of 2, so the 2 one is strictly dominated, but still we assign some probability to the strategy 2 also. So the statement B is incorrect. So statement A is correct as discussed in the lectures, whereas statement B is incorrect as all strategies get some non-zero probabilities in quantum response equilibrium. So A is correct, but B is false. So hence option B is correct. Option B is this. So hence option B is. Okay, then. So this was just all the questions which I had for the day. So I think a lot of the questions were more or less theoretical questions only. There were some numericals like this area one and the one which we discussed here, the asymmetric matching penny scheme. But other than that, I think a lot of today's lecture was focused on theory. We also discussed the theoretical proofs, the high level idea of them and everything. Maybe I should just remove this quantum response. This area one and the one which we discussed here, the asymmetric matching penny scheme. But other than that, I think a lot of today's lecture was focused on theory. We also discussed the theoretical proofs, the high level idea of them and everything. Maybe I should just remove this quantum response part because it may cause some confusions. So yeah, and yeah, a lot of questions were based on like theory only here because the lectures were also more or less theoretical. But all of this is also very important, guys, this theory part also, because this theory is what leads us to like good models and everything. Like, why should one believe that one can model things using best response strategies as Nash equilibrium? Or why is this quantum response relevant? Like, it's this solid foundation of theory which says that even if you do these kinds of things, their existence ensures that we'll never hit some hurdles while trying to model stuff using these kinds of things. So, okay, then, so this was just a high level idea. Okay, so I guess this is it from my side, guys. And since no one is in the session in person, so I guess we won't be taking any doubts. So hopefully I'll see you guys in person next time. So we are done for the day, and like I'll hopefully see you guys next time in person. Same timings, Monday 6 to 8 p.m. And yeah, hopefully we'll see you guys there. So for now, I'll be closing the session and goodbye, guys.